Lesson 2.4, Real Zeros of Polynomial Functions. You can find this lesson on page 197 in your books. To start off this lesson, we're going to do an example of polynomial long division. It's basically the same process you did when you first learned long division way back in 4th or 5th grade. Okay, now we're just applying it to polynomials using those same basic ideas. So for example, suppose we're taking 3x cubed plus 5x squared plus 8x plus 7. That is our dividend. And we're dividing that by 3x plus 2. That's called the divisor. To start this, we want to look at our divisor, 3x plus 2. And we're going to look at the first term, 3x. We need to determine how many times does 3x go into 3x cubed. Or another way to think of that, what can I take times 3x to get 3x cubed? And we can take an x squared times 3x to get 3x cubed. And I'm going to write that above my other x squared terms, just so I keep all my terms in line vertically. Once we determine that, now we're going to take our x squared times our 3x in our divisor, which is 3x cubed, and then we're going to multiply our x squared by 2. And x squared times 2 is 2x squared. Once I write these values down below, we are subtracting those. So if I subtract those from what I have above, 3x cubed minus 3x cubed is 0. 5x squared minus 2x squared is a positive 3x squared. Then we bring down everything else. We have plus 8x plus 7 at the end. And now we're going to repeat this process, except this time we're going to look at our 3x in our divisor and determine how many times does that go into 3x squared. Or what can I take times 3x to get 3x squared? We can multiply that by a positive x. So again, I'm going to repeat this process. We take x times 3x to get our 3x squared. Take x times 2 to get 2x. And again, we're subtracting whatever those values are. So what we're left with now, this is 0. 8x minus 2x is a positive 6x. Bring down our plus 7. So we need to determine how many times does 3x go into 6x. It goes in there 2 times. So we have a plus. We have plus 2 at the end. Repeat that same process. 2 times 3x is 6x, and 2 times 2 is 4, and we're subtracting those values. What we're going to be left with here, 6x minus 6x is 0, 7 minus 4 gives us 3. This becomes our remainder. Because if we try to repeat the process we've been doing, the 3x in our divisor will not go into 3. It's a higher degree term. So how we take this remainder of 3, we bring it up to the top, and we have plus 3 divided by our divisor, which is 3x plus 2. So when we take 3x cubed plus 5x squared plus 8x plus 7 and divide it by 3x plus 2, we get x squared plus x plus 2. This main part is called the quotient. Okay, quotient should be a familiar term whenever we're dividing something. This end part is our remainder. Many times you'll have a remainder of 0, but if you have something other than 0, you take what that value is you end up with and write it divided by the divisor. That is polynomial long division. This lesson has quite a few theorems that we need to discuss. The first theorem is the remainder theorem. The remainder theorem says if a polynomial f of x is divided by x minus k, then the remainder is r equals f of k. So we could go through, if you see the example below, we could go through polynomial long division, find out what our remainder is. But by this theorem, it says if we simply take the value of the function at our k value, that will be our remainder. So if we're taking our polynomial, in this case f of x would be equal to 3x squared plus 7x minus 20. We're dividing that by x plus 4. So notice in our theorem definition, it's x minus k. So if this is a positive 4, we need to think of our k value as k being equal to negative 4. So what we need to do is take the value of this function at negative 4. So we have 3 times negative 4 squared plus 7 times negative 4 minus 20. Negative 4 squared is 16. 16 times 3 is 48. 7 times negative 4 is minus 28 minus 20. Simplify this down. Whoops. If you simplify correctly, you get a remainder of 0. So if we would have gone through polynomial long division like we did in the first example, we would have gotten a remainder of 0. So the remainder theorem saves us a lot of time, because the remainder theorem leads us into what we need to do in our next example, and we also have another theorem that goes along with it, and that is called the factor theorem. Okay, the factor theorem says a polynomial function f of x has a factor of x minus k if and only if f of k is equal to 0. So I'm going to go back to the last side. When we took the value of f of negative 4, we ended up with f of negative 4 is equal to 0. The value of our function at negative 4 was equal to 0. So that meets the definition of the factor theorem. F of negative 4 was equal to 0. Okay, f of negative 4 is equal to 0. So by this definition, that means x plus 4 would be a factor of that original polynomial. Okay, a lot of terminology going on here, the remainder theorem, the factor theorem. This is all leading into having an understanding of what a factor of a polynomial is, what is 0, what a solution, what an x-intercept is. And that is what our fundamental connections are. For a polynomial function f and a real number k, the following statements are equivalent. The first one, x equals k is a solution or root of the equation f of x is equal to 0. K is a 0 of the function f. K is an x-intercept of the graph of y equals f of x. And x minus k is a factor of f of x. Okay, so the solution or root is the same thing as the 0, is the same thing as the x-intercept. If all those are true, that's implying that x minus k would be a factor, all relating and referring to the same idea. Next thing we're going to talk about is synthetic division. Okay, trying to accomplish the same thing we just did with polynomial long division, except synthetic division is kind of a neat trick we can do. A lot of people find it easier to use, but we can only use it in certain circumstances. Okay. On a side note, a good movie just came on, Lord of War. So if I start not saying words is probably because I got distracted by the movie. Okay, if you ever want to watch a good movie, Lord of War. It's got Nicolas Cage, pretty good movie. Back to synthetic division. We got 2x cubed minus 3x squared minus 5x minus 12 divided by x minus 3. The only way we can use synthetic division is if what we're dividing by is a linear binomial. Linear meaning the exponent on our variable is 1, binomial meaning 2 terms. So it must be a linear binomial for this to work. Okay. And what we're going to do is take the coefficients of our polynomial and list them. So we have 2, negative 3, negative 5, and negative 12. And then we're going to take our value of 3. It is x minus whatever that value is. In this case, it'll be a value of 3. And we're going to write that out in front. So, step 1, we take our first coefficient of 2, and we're going to drop that down. Bring that straight down. Now we're going to take our 3 and multiply it by 2. 3 times 2 gives us 6. Now we're going to add these numbers vertically. Negative 3 plus 6 is 3. Now I'm going to take my 3 times my 3. It gives me a value of 9. So we have negative 5 plus 9 gives us 4. We're going to repeat this pattern. 3 times 4 is 12. Negative 12 plus 12 is 0. So this last number we end up with, that is our remainder, just like we would do if we had polynomial long division. So if that gives us a remainder of 0, now we need to determine what do these coefficients, or excuse me, what do these numbers at the bottom represent? Okay, because we took 2x cubed minus 3x squared minus 5x minus 12 divided by a linear binomial of x minus 3. These numbers 2, 3, and 4 stand for the coefficients of our quotient. So if we started with an x cubed and we divided it by an x to the first, 3 minus 1, we would end up with an x squared. So this becomes the leading coefficient, 2x squared plus 3x plus 4. Okay. So when you use synthetic division, the number you end up with at the bottom, it's always a degree 1 less than what you started with. So just take your x cubed, subtract 1, you're going to have an x squared. So you end up with 2x squared plus 3x plus 4. That is our quotient with a remainder of 0 using synthetic division. I'm going to quickly go through another example of synthetic division, because in this problem we have a little trick, or not a trick, but something we need to be aware of when we go through these problems using synthetic division. This time we have 3x cubed plus 4x minus 7 divided by x minus 2. So if I bring down my coefficients just like I did last time, coefficient of 3, notice I don't have an x squared term, so I need to put a 0 in that place value. When you're going from highest degree to lowest degree, if you're ever missing one of your terms, you need to put a 0 in that place. So we have 0 in for our x squared, we have a 4, negative 7, and we have a positive 2 out in front. Remember, it's x minus that number. So if I bring down my 3, 2 times 3 is 6, 0 plus 6 is 6, 2 times 6 is 12, 4 plus 12 is 16, 2 times 16 is 32, 32, and then negative 7 plus 32 is a positive 25. Okay, so notice this time we didn't get a remainder of 0, So how we write that is this would be, notice we started with an x cubed again, so this would be 3x squared plus 6x plus 16 plus 25 divided by our divisor of x minus 2. So just like polynomial long division, one synthetic division, if you have a remainder, you write it the same way. You take that remainder divided by the divisor. The last theorem in this lesson is the rational zeros theorem, also called the rational roots theorem, which should make sense. We just talked about zeros and roots referring to the same idea. Suppose f is a polynomial function of degree n greater than or equal to 1, with every coefficient being an integer. Okay, so this theorem only applies if all the coefficients are integers. No fractions or irrational numbers can be included. Let p represent the factors of the constant term and q represent the factors of the leading coefficient. Possible rational zeros are of the form x equals p divided by q. And this is something we touched on in Algebra 2. The rational zeros theorem simply tells us the possible rational roots we could have. It doesn't tell us exactly which ones are the zeros of the function or the polynomial. It tells us all of the possibilities. Alright, so we're going to go through an example to show you how this theorem applies and how it benefits us. Now we're going to use the rational zero theorem for f of x equals 2x to the fourth minus 7x cubed minus 8x squared plus 14x plus 8. We're going to use that theorem to find all of the possible rational roots for this polynomial. So first thing we need to do is take all of our factors of our constant term. So factors of 8. We get plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8. Okay, we have to have plus or minus for each of them because we could take negative 1 times negative 8 to get a positive 8. So those are all of the factors for our constant term. Now we need to take the factors of our leading coefficient, which are plus or minus 1, plus or minus 2. So now we're going to simplify all this. We need to take every number in the numerator divided by both numbers in the denominator. So if we take every number in the numerator divided by 1, we get plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8. Now we have to take every number in the numerator and divide it by 2. So if we take 1 divided by 2, we get plus or minus 1/2. Well, if we take 2 divided by 2, that is plus or minus 1, which we already have. 4 divided by 2, 2, which is what we already have that. And 8 divided by 2 is 4. We have that as well. So these are all of the possible rational roots for this polynomial. That doesn't mean these are all going to be rational roots. None of them may be. These are all of the possibilities, these 10 different numbers. So now we could use each of these numbers we came up with. We could use synthetic division and determine if all of those are actually zeros to the polynomial. If we went through synthetic division and got a remainder of 0, that implies that is a root. We could go through and do that 10 times. But to save us a little bit of time, we should graph this polynomial and try to determine where these zeros may be, give us a better idea. Okay, so we click the graph button and graph this. It looks like we have 2 zeros that are going to be at negative x values and 2 that are going to be positive x values. One that we can look at that looks pretty easy to determine is at x equals 4. It looks like our graph crosses right at x equals 4, so that should be one of them we try to determine. So we're going to use synthetic division to determine whether or not 4 is actually a root to this polynomial. So our coefficients are 2, negative 7, we have negative 8, 14, and 8. And we're going to check whether or not 4 is one of those. So we bring down our 2. 4 times 2 is 8. Negative 7 plus 8 is 1. Multiply, we get 4. Negative 4. 4 times negative 4 is negative 16. So that gives us negative 2. 4 times negative 2 is negative 8. Gives us a remainder of 0, which is good. So that implies that 4 is one of our factors to our polynomial. Okay? So 4 is one of our factors. So that means that original polynomial, if 4 is a 0, that implies that x minus 4 is a factor. Okay? And now we're going to use these numbers as the coefficients for the polynomial we have left. Remember, if we started with an x to the 4th, now this is going to become 2x cubed plus x squared minus 4x minus 2. So now we're going to look at that. 2x cubed plus x squared minus 4x minus 2. And we're going to go back to our graph and see if we can determine whether or not another one of those numbers is one of our roots. Okay, if we look towards the left side of the graph now, between 0 and 1, it looks like it crosses between there right in the middle, so negative 1/2. If we go back up to the top, remember negative 1/2 is one of our possibilities for our rational root, just like positive 4 was one of our possibilities. So since they're one of our possibilities when using the theorem, and it looks like that's where it's crossing on the graph, that is where we should check using synthetic division. So if we go back up here, now we're going to use these coefficients we have left from our polynomial. So 2. We have 2, 1, negative 4, and negative 2. The number we want to check is negative 1/2. So if we bring down this 2, 2 times negative 1/2 is negative 1. That's 0. We get 0. Negative 4 plus 0 is negative 4. Negative 1/2 times negative 4 is a positive 2. And we get a remainder of 0. Okay. Remember, this was an x cubed function, so that means we have our factor of x minus 4 from above. This had a remainder of 0, so that means x plus 1/2 would be a factor. And what we have left is 2x squared minus 4. Again, we could try to go through synthetic division and check and try to get rid of 2x squared minus 4. But now we got this down into a quadratic function that's a lot easier for us to work with. Okay, we work with quadratic functions all the time. So we can try to factor this. Okay, if we look at that, what do those two terms have in common? They have a factor of 2 in common. So I'm going to take that factor of 2 and I'm going to pull it out in front of all of these factors. Now we're going to be left with x squared. Whoops. If we take a 2 out of there, there should be x squared minus 2. Also, something we're going to simplify, I'm going to multiply this 2 through to that factor just so we can get rid of that 1/2, and it makes it a little easier to simplify. So now we're going to have x minus 4 times 2x plus 1. We distribute that 2 through. X squared minus 2. That is actually a difference of 2 squares. Okay, you're thinking 2 is not a perfect square. Well, in terms of what we talked about in Algebra 2, you would be right. Okay, but now we're getting into pre-calc. We can start thinking of these concepts a little more deeply. 2 is the same as radical 2 times radical 2. So it actually is a perfect square, which means we could factor this into x minus radical 2 times x plus radical 2. So now we have all of our factors. Now we would take each of these factors and set them equal to 0. So x would be equal to 4. If we set 2x plus 1 equal to 0, we would get x equals negative 1/2. And if we set each of these factors equal to 0, x minus radical 2 equals to 0. So x equals radical 2, and x plus radical 2 equal to 0. So x equals negative radical 2. So, using the rational zero theorem and synthetic division, using a graphing calculator, using many tools, we found all of the zeros for that polynomial function. 4, negative 1/2, radical 2, and negative radical 2. Looking at these zeros, if we look at 4 and negative 1/2, both of these are rational zeros. If we look at radical 2 and negative radical 2, those would be irrational zeros. Remember, rational numbers are numbers that are integer divided by integer. Irrational numbers, anytime you have a radical, pi, the letter e, when we use that as a number in exponential functions, those are all irrational numbers. There's been a lot of information so far in this lesson, but this is the last thing we're going to talk about. Okay, on the bottom of page 202, there's a table for the definition of upper and lower bounds for real zeros. You can copy that table down in your notes. I think it's going to be a little confusing for you, so we're just going to go through this example, and I think it should make a little more sense. So what we're going to do is prove that all of the real zeros of the polynomial f of x equals 2x to the 4th minus 7x cubed minus 8x squared plus 14x plus 8 lie in the interval from negative 2 to 5. So what we're going to do is use these two endpoints, negative 2, and we're going to use synthetic division. So we have 2, negative 7, negative 8, 14, and 8. Drop down our 2. We get negative 4, negative 11, positive 22. This would be negative 8 plus 22 is 14. Negative 2 times 14 is negative 28. 14 minus 28 is negative 14. Multiply that through 28 plus 8 is 36. What we're looking at here is if we check this negative 2, if it's going to be a lower bound, all of the signs along the bottom row need to alternate between positive and negative. We have a positive, positive, and positive, and negative. If those are alternating, every number that indicates that negative 2 is a lower bound. Okay, so using synthetic division to prove that it's a lower bound. Now we're going to check whether or not 5 is an upper bound using the same numbers. So 5 times 2 is 10. Get a positive 3, 15, 15, and negative 8 is a positive 7, 35, 49. Oh, this is getting to be a large number. 5 times 49, 5 times 50 is 250, 250 minus 5 is 245, 8 times 245, 253. Okay? What we're looking at, if we're trying to prove whether it's an upper bound, every sign must be the same. Okay? And not only must they be the same, they have to be positive or zero. They can't be negative. So this would be an upper bound. Okay? So we have to prove whether or not they lie in the interval. We take our two endpoints. -2 is going to be our lower bound. 5 would be our upper bound. And we use synthetic division to check that. If the signs alternate, that's a lower bound. If the signs are all non-negative, meaning positive or zero, that is an upper bound. So this concludes lesson 2.4. You can go ahead and get started on the homework.